Okay, here we're going to discuss an interesting example. This example is about maximizing utility function. So in this example, our goal is to maximize a utility function that depends on x, y, and t, where x is the unit of food, y is the unit of clothes, and t is the time for leisure. Okay? But then you have some constraint. The first constraint is what we call budget constraint. Okay? Budget constraint. Budget constraint. Because, well, you spend, well, food and clothes cost money, and each of them costs $250 and $350 respectively. So the total cost is given by 250x plus 350y, and each day, according to the question, you are only having a budget of 200 plus 400 times 16 minus t dollars. And then why this is a variable? Because, well, the question tells you that you spend this amount of hours on part-time job with wage of 400. So these are the extra money you earn by doing part-time job. And then what else? Okay, t does not exceed 16. And then you have the standard non-negativity constraint, because clearly clothes, food, clothes, and time, they cannot be negative. So you have the standard non-negativity constraint. Non-negativity constraint. Okay, let us look at part A. Part A. Write down the Kuhn-Tucker Lagrangian for this problem, and also all the first order condition in Kuhn-Tucker's formulation. So let us write down the Kuhn-Tucker Lagrangian. The notation is L tilde, which is given by the objective function. So the function you try to maximize is u, okay? Let me just call u. And the minus, well, in this case, you have two inequality constraints. The first one is the budget constraint. The other one is t less than or equal to 16. So this is the other one. So you need two Lagrange multiplier, number 1, and then write down, so 250x plus 350y minus 200 minus 400 times 16 minus t. Okay? And then another constraint that is given by t less than or equal to 16, so you should put t minus 16 here. And in Kuhn-Tucker formulation, you can ignore all the non-negative constraints. And how about the first order condition in Kuhn-Tucker formulation? So Kuhn-Tucker first order condition. So equality, what are the equalities? They are all given by complementary slackness. Or in other words, okay, so you have x times L tilde differentiate with respect to x, which is x, times differentiate this function with respect to x, you get, well, differentiate u with respect to x, you get ux. And the minus number 1, differentiate this, differentiate this with respect to x, die, okay, you have only 250 survived. And the minus, well, you have nothing else, because the last guy have no x, so everything died. So you want this to be 0. And then you also need to do it for y. And then if you differentiate with respect to y, you get uy minus lambda 1, 350, and then equals 0. And then you have also a variable called t, and then that becomes t times differentiating with respect to t, you get ut. And this guy, differentiate with respect to t, well, die. The only guy that survives is this become minus 1, so you get plus 400. So minus lambda 1, sorry, let me use uniform color. 400. And the minus number 2, differentiate with respect to t, you get 1, so times 1 equals 0. And also you have the usual complementary slackness that come from this expression, and this expression equals 0. So lambda 1, maybe I need more space, so let me write like this. Lambda 1 times 250x plus 350y minus 200 minus 400 times 16 minus t equals 0. And also lambda 2 t minus 16 equals 0. So these are all the equality condition. How about inequality? Inequality condition, firstly, you have all the partial derivative of L tilde with respect to x, y, and t are less than or equal to 0. So, for example, L tilde x, which is ux minus lambda 1 250. So ux, let me write down, L tilde x equals to ux minus lambda 1 times 250 is less than or equal to 0. Ly tilde, which is we calculated here. Sorry, we calculated here, which is uy minus lambda 1 350 less than or equal to 0. And Lt tilde is ut minus lambda 1 400 and then minus lambda 2 less than or equal to 0. And then also all the lambdas, all the Lagrange multiplier are non-negative. So lambda 1 is greater than or equal to 0. Lambda 2 greater than or equal to 0. And finally, the given set of inequality constraint. So finally, you have the first inequality constraint is 250x plus this less than or equal to. So the budget constraint. And then you have the t less than or equal to 16. And then the non-negative constraint, x greater than or equal to 0, y greater than or equal to 0, and z greater than or equal to 0. Okay? So if you want to be more organized, so these are all the equality coming from complementary stateness. This three come from negativeness of L tilde xi. And this come from positiveness of the Lagrange multiplier. And finally, these are the given inequality constraint. Okay? Yes, there are many conditions. Don't miss them. When you write down slowly. Make sure that you don't miss any of them. Okay, part B. Part B, explain why this constraint is always binding at any solution to the first order condition. So, part B. I want to show that this constraint is always binding. How do I show that? Let us prove it by contradiction. So suppose by contrary, we have 250x plus 350y is strictly less than 200 plus 400 times 16 minus t, so i.e. not binding. I want to show that it's always binding. So let me suppose it's not binding and see what kind of disaster happened. If this not binding, then what happened to, well, if you look at this set of equation, obviously the only one that is relevant is this one. In particular, because you have this inequality, that's why this guy is non-zero. If this non-zero times lambda 1 equals 0, it forces lambda 1 has to be 0. That's the idea. So let me label the equation. You have equation 1, 2, 3, 4, 5. So by equation 4, we have lambda 1 equals 0. But what's the problem? If lambda 1 is 0, where do I have lambda 1? Well, I have lambda 1 in this equality. And also I have lambda 1 in this inequality. But if lambda 1 is 0, look at this. Okay, look at this. Then we have Lx tilde equals to ux. Because lambda is 0, right? Lambda 1 is 0, so this die. And this become this less than or equal to 0. Is that possible? Well, look at the question. the question actually specifically tell you that it's known all the partial derivatives are strictly positive. Therefore, this is a contradiction, because which contradicts with the given fact, the given information that Ux is strictly positive. So we have a contradiction. That means that what we assume in the beginning is incorrect. So we assume it's not binding and it must be wrong. Hence, the constraint 250x plus 350y less than or equal to 200 plus 400 times 16 minus t must be binding. Okay, so that's the proof. Okay, the proof uses beautifully the one of this inequality condition and also the given information. So that's it. Okay, let us look at the last part. The last part, now you're given a maximizer to the problem. So a maximizer means, in particular, it's a solution. It's a solution to the first order condition. And what else do you know about this maximizer? You know that the x coordinate, x star, is strictly positive. And y also strictly positive, and t is strictly between 0 and 16. Okay? And now you're asked to show that you have this equality. Now for some of you, maybe it's not new to you, this equality, because we actually proved something similar in Calculus 3 in one of your worksheets. But if you don't remember that, it does not matter, okay? We will do it from scratch. So let us do it per se. So actually, this problem is easier than you think, because, well, you know that x star, y star, t star satisfy this bunch of first order condition. In particular, if you look at the first one, because I know that x star, okay, x star is strictly positive. So in particular, it's not 0. So for the product to be 0, you need the second half to be 0. So since x star is strictly positive, so the first equation 1 implies Ux minus 250 lambda 1 equals 0. And similarly, you can do the same argument for the second equation and the third equation. So since when y is y star is strictly positive, so the second equation implies when you have a product that becomes 0, at least one of them is 0, but this is not 0, so this must be 0. So you have uy minus 350 number 1 equals 0. And since t equals t star is strictly positive, so the third equation implies ut minus lambda 1 times 400 minus lambda 2 equals 0. But that's not all. That's one more that you know, because t is not only positive, also is strictly less than 16. So since t equals t star is strictly less than 16, so the equation here, the fifth equation here, says that t star minus 16 cannot be 0. So that means that lambda 2 has to be 0. So 5 implies lambda 2 has to be 0. Well, if you combine all this together, so combine this, then we have lambda 1 equals to what? On one hand, by the first equality, lambda 1 equals to ux over 250 250. Ux over 250. But on the other hand, lambda 1, according to the second equation, also equals to uy over 350. And finally, according to this equation, what is lambda 1? Lambda 1 it looks messy. Good, but lambda 2 is 0. I can forget about it. So according to this equation, I have lambda 1 equals to ut over 400. So in particular, these three quantities are equal when, so at xyz, so xyt equals to x star, y star, t star. And we're done. That's it.